Hello and welcome to CE3105 Mechanics of Fluids Lab here at Texas Tech University. In this lab, we're going to talk about pump characteristics. We're going to look at operations of a single pump and series and parallel configurations. So let's begin our discussion talking about pumps. What are pumps? Well, pumps are devices that are used to add energy. So typically pumps convert electrical energy to mechanical energy, which then is converted to hydraulic energy, or that energy is supplied to water. There are many types of pumps in the market. They can be broadly classified into two types, dynamic pumps and positive displacement pumps. Dynamic pumps are the most common types of pumps. And in a dynamic pump, the energy of the fluid increases from the inlet to the outlet of that dynamic pump. Positive displacement pumps work on a slightly different idea. And what they do is they have an expanding cavity on the suction side, which causes the water to flow in, and then a collapsing cavity on the outlet, which causes the water to flow out, albeit at an increased pressure. So positive displacement pumps sometimes can be used without electricity or for smaller volumes, but for most purposes, we make use of dynamic pumps. Pumps have widespread use in civil engineering. Pumps are used to add energy. We add energy for a variety of different reasons. Most of the times we add energy because we want to increase or overcome a potential head, that is, try to move water uphill. We want to sometimes increase the pressure of water. Water treatment systems in particular need to supply water at a certain pressure to the households. And as water moves, there are friction losses which cause water to slow down or lose pressure, and pumps sometimes are added, so pumps are used to add pressure to that water so that the water can be supplied at sufficient pressures. Of course, we can also use pumps to increase the speed of flow or get more throughput. And pumps are often used to compensate for energy losses in pipes, that is, overcome friction and other minor losses that are encountered when we move water through large distances. So there are a variety of reasons why we use pump. The basic idea in all of these applications is that we want to take the energy that's provided by the pump, or the mechanical energy that's provided by the pump, and convert it into some form of hydraulic energy, either to increase pressure, increase the velocity, or increase the elevation, or all of it, overcome friction. The most common types of pump that we use are centrifugal pumps. Centrifugal pumps are a type of dynamic pump. And the centrifugal pump consists of an impeller, which are basically blades that rotate around a shaft, or a drive shaft, which is connected to an electrical supply. So the shaft rotates, which causes the impeller to rotate. Water enters the pump, so there is inlet or suction of water into the pump. And as the impeller rotates, the energy of that impeller is added to the water, and then the water moves through the circumference and then discharges outside. So typically, this type of a configuration has a volute chamber, where the velocity, the cross-sectional area, increases towards the outlet side, and which causes the pressure to stabilize, and then the water moves out at some constant pressure. Okay, so typically an impeller is connected to a motor. It's made to rotate at very high speeds. Of course, the speed of that impeller is an indication of how much energy we are going to supply to the pump. And of course, the diameter of the impeller also plays an important role in supplying that energy to the pump. So the water enters in an axis perpendicular to the impeller, and due to suction, and then it acquires energy from that impeller and then flows out. So most of the times we use this volute chamber, which is basically a curved funnel type configuration with increasing cross-sectional area. But some pumps also make use of a constant, or a diffuser vane, or a diffuser type case, where the impeller blades are slightly curved, they supply water, and then it discharges out. Depending on the geometry, we can use either a volute chamber or a diffuser chamber for our centrifugal pumps. So in a hydraulic pump, the key concept to know about pumps is that the impellers cause rotation, and that rotation produces mechanical energy, which is supplied to the water. So we are essentially converting mechanical energy to hydraulic energy. Of course, we need electrical energy usually to convert that electrical energy and create that mechanical energy with which the impeller is rotating. Just as a brief refresher, power is the rate of doing work or energy per time. So we are doing an energy balance here, and we say that the input power to the pump is equal to the mechanical work of the impeller. So from work energy theorem, we know that the mechanical work done over a time is equal to power, or the input power of the pump, and we can calculate that using this formula, which is 2 pi nt over 60, where n is the rotational speed, or the number of revolutions per minute of this pump, and then T is the torque. So torque is the force times distance. So we have essentially 2 pi r, which is the circumference, or the water, that is the water moving through the circumference, times n, which is the number of times the impeller rotates. So that is the rotational speed. And the torque, the other term of the torque, is that force. And of course, we use the 60 in the denominator to convert our revolutions per minute to from minutes to seconds. So we can calculate the input power as 2 pi nt over 60, where n is the rotational speed in revolutions per minute, and t is the torque. And on the water side, once the water is added to, or once that energy is added to that water, we can look at Bernoulli's equation before and after the pump. And so before the pump, we have PA over gamma plus VA squared over 2G plus ZA. This is your pressure head, your velocity head, and your potential head, plus the energy that's added to the pump here. Is equal to PB over gamma plus VB squared over 2G plus ZB plus any friction loss or other minor losses that you may have on the pump. So if I collect the head due to the pump and loss due to the pump, on one side you can see that the net head due to the pump, which is minus the friction losses or minus the losses, is equal to your total head at the outlet of the pump minus the total head at the inlet of the pump. If we further go and say that the pipe diameter is the same, then my velocity B is equal to velocity A, and if the elevation differences before and after the pump are not significant, then we can neglect our ZB and ZA and assume they are approximately the same. So the total head due to the pump is essentially equal to the difference in the pressure heads, and if I take that pump head and multiply times the specific rate, I get that that is equal to delta P, or the change in pressure. The output of the pump can be calculated as W2, which is equal to HP times gamma, which is the differential in pressure times the flow rate, and that gives us force per distance per time type units, or energy per unit time units, or the power. And so W2 is the output of the power, and this W2 typically is a little bit less than W1, and the reason for that is because the pump is not completely efficient. It does not convert all of the mechanical energy to hydraulic energy. There is some loss due to turbulence, due to heat, and sound and other factors. So not all of the energy that is supplied by the impeller is added to the water. Of course, the efficiency of the pump is this W2 over W1, and the closer it is to 1, the better the pump it is. So how do we use pumps in civil engineering? So typically we look at our system. Our system is the system where we want to supply energy, and we create what's called as a system resistance curve. And what this system resistance curve does is, as our flow rate increases, our need for that head keeps on increasing. So we need to add more and more head through the pump, or energy through the pump, as our flow rate increases in our system. A pump curve is something that a manufacturer supplies, and the pump curve essentially tells us how the pump operates. So typically at very low pressures, the pump is able to supply, at very low flow rates, the pump is able to supply a lot more head, and then as our flow rate increases, the pump curve keeps declining, or there is less and less head that's supplied by the pump. So the point where the system resistance curve intersects with the pump curve is where we get the operating point. So knowing our system, we create our system resistance curve or our system curve, and then the manufacturer provides the pump curve. And usually we know the flow rate or the operating point where we want this to work. So we try and find a pump that will provide us that flow rate. So if I had a curve of a pump that just went this way, then it may not be sufficient for us. So it may only provide us with a much smaller flow rate. So we have to select a pump that gives us the flow rate that we want. So that's the basic idea behind designing a pump. And of course, a lot of times a single pump may not be sufficient for us. So either we use pumps in series or pumps in parallel configuration. We use pumps in series when we want to add energy without changing the flow rate. So this configuration is used when an individual pump is not enough to supply all the energy. So we put two pumps in series and increase our energy that way. And then, but we are not changing our flow rate. So we can again apply Bernoulli's equation. The flow rate remains the same. I have point A and point B and point C. There is a pump between point A and point B, and there is a pump between point B and point C. Typically, these pumps are so close to each other that that there is very little loss assumed between the pumps. So again, if I apply my Bernoulli's equation at A, I have PA over gamma plus VA squared over 2G plus ZA plus HP1. This is the power or the head that supplied the total energy, the energy head that's supplied by pump 1, and that's it to PB over gamma plus VB squared over 2G plus ZB plus HB2, which is the power supplied by the pump 2, which is equal to PC over gamma plus VC squared plus ZC. Again, if we assume that our PB is, so basically we can come back and say that our again, if we neglect our velocity heads because the pump has the same diameter and it has the same flow rate going through, so the velocity is constant, so I can cancel out my velocity terms. And then if the pipe is horizontal to the ground, then there are very little elevation differences due to pumps in series. So if we neglect that, then the total head supplied by pump 1 plus pump 2 is equal to PC over gamma, which is the pressure that I measure after the last pump in series, minus PA over gamma, which is the pressure entering or the pressure before the first pump that's in the series. So that's how I can calculate the total head or the total amount of energy that is added by the pumps. So again, pumps in series are used when one pump is insufficient to provide all the energy, and so we want to increase the pressure, but we really don't want to increase the flow rate. So that is, we are moving water and we want to move it uphill or move it someplace else, or we don't have water of sufficient pressure, so we want to increase the pressure because we want the water to discharge as a jet or reach a certain place with a certain amount of pressure, as is the case with water supply systems. So what happens in pumps in series? Again, we have flow rate Q and then total dynamic head. So the one pump would only, for a given flow rate, the one pump would only supply H1. But if we have two pumps in series, then we would get both H1 plus H2, which is H2, which is the total head. So we increase the head without increasing the flow rate. So that's what a pumps in series do. Pumps in parallel, you use pumps in parallel if you want to increase the flow but not increase the energy. So this is the opposite case of pumps in series, or you can think of. So we have flow coming into the system Q. and then we have that flow being split into Q2 and Q1. Q1 flows through pump 1, and then Q2 flows through pump 2. Energy is added to Q1 through pump 1, and energy is added to the Q2 portion of that flow rate through pump 2, and they both add up. They both again are mixed, and then the Q flows out together. So if the pumps share the same suction and discharge line as I show here, they're sharing the same suction line and the same discharge line, then they must have the same impeller diameter and the speed, because the head at C should be equal to the head at B. So the pumps are adding energy, but they're adding the same amount of energy. So if I were to draw the energy grade line up on the top, it will increase, but it'll increase the same across the two pumps. Okay, so typically when you have pumps in parallel, you have a little bit more of piping that's necessary, so there is going to be some friction losses in this case that cannot be ignored in real world applications. So the two pumps will slightly give you a lower amount of water. So if I had the same pumps, I can't double the amount of water, it'll be slightly less. Again, if I look at my pump operation, again, if I had only one pump, that pump would only supply, let's say my operating point is at B. You see that at B, I get a flow rate of Q1. But if I have two pumps in parallel for that same head, I can extend this B all the way and get a flow rate Q2, which is much greater than Q1. So the advantage of adding two pumps in series is that you get more flow with pump B. And as you can notice, this is the system resistance curve that I'm plotting. If I only had one pump, I would be restricted to some flow here, but if I add two pumps, I can go all the way to this point. So it kind of shows how to design two pumps in parallel. And of course, there is volume increase as I go from one pump to two pump without really an increase in head at any given point. The other things to know is that we characterize pumps, or sometimes we have to scale up pumps. So we use dimensional analysis and similarity conditions. There are 3 or 4 dimensionless numbers that are useful when it comes to designing pumps or scaling up pumps. We have the flow coefficient, the head coefficient, the power coefficient, and the Reynolds number. These all depend upon the impeller diameter D, as well as the angular velocity n, which is given in radians per second. Keep in mind that 1 revolution is equal to 2 pi radians. So 2 pi n over 60 would be revolutions per minute that are converted to radians per second. So that's what we did when we calculated the pump power, and we need to use that number here. So n here stands for radians per second and not revolutions per minute, as we saw in the previous calculation of the power. What are these dimensionless groups used for? So they can be used for scaling up of designs. So if I want to change the pump speed N and impeller diameter D, I can see how I can get a new flow for an old flow. So the denominator is what I've measured, and Q2 is what I aspire. So basically you can see that my flow rate scales up as the cube of the impeller diameter. So a small change in impeller diameter can get me a lot more Q because it's a cubic power. But if I keep my impeller diameter the same, then essentially the flow scales up with number of revolutions. So the more the number of revolutions, the more the flow rate. Similarly, the head, if I want to predict a new pump head by changing the pump speed N and impeller diameter D, again, you can see that they have the same influence on pump head. And then finally, I can use the power, which is the horsepower of the pump, and that scales up again as the cube of the number of revolutions. But as the 5th power of the impeller diameter. So again, impeller diameter, small changes in impeller diameters can considerably change the energy or the power that's produced by the pump, as well as the flow rates that are produced by the pump. So pump characteristics help us, like, scale up our designs from laboratory scale to real world scale. So they are extremely useful during design. So what we have in our laboratory is a pump setup. We have two pumps, pump 1 and pump 2, and we have piping and valves. And this valve essentially is a two-way valve which we can move to make the flow go either to just pump 1 or from pump 1 to pump 2 in series, and then from pump 1 to pump 2 in parallel. And then we have a delivery valve which we use to control our flow rate. So we change our flow rates using this delivery valve, and then we use the data acquisition system that's provided to read out the torque, the number of revolutions per minute, the impeller speed, as well as impeller speed, as well as the various pressures along this pipe configuration. We also have a Venturi meter up here, which we use to measure our flow rate, and our Venturi meter, the flow rate equation is given to us here. CD is the discharge coefficient, and the A1 and A2, you're given the pipe diameters in your handout. So you use that to get your A1 and A2, the density of water, for which you need to know the temperature. And then this delta P, which is the change in the pressure between the Venturi meter, which are these two lines here, is measured again from the digital readout that we have. So you measure delta P, and you know everything else, and that's the way you calculate flow. And then you calculate your flow, and then you make required calculations for your single pump, pumps in series and pumps in parallel. And then, of course, you can also acquire all this data using a computer, and we're going to demonstrate to you the data acquisition software that's typically used when we want to do online measurements, or continuous measurements of pumps in operation.